Okay, so question 2. We have a tension in the line of 720 newtons, angle of 50 degrees. Find the vertical component of the tension. Okay, so we've got the vertical component right here. I'm going to label the horizontal component as well. What's the rule? It's a cos if you move through the angle, so this is sine. So this is 720 sine 50. What does that come out to then? 720 sine 50 comes out to 551. So 720 sine 50 equals 5, let's call it 552 newtons. 552. The kite boarder has a mass of 58 kilograms. Find the normal reaction of the board on the kite boarder. Okay, so let's imagine this is our kite boarder, and he's on this board here. Label the forces. Well, we know that the tension pulling upwards is 552, and we also know that the weight downwards is 58g. So this is mass times gravity. That's 569. Oh, 569. So there must be, it's in equilibrium, right? The forces are balanced. So there must be a kind of missing little force here. Who knows how big it is? Well, we'd work it out. 569 minus 552 minus 552 gives me 17 newtons. So the normal reaction force from the board should be about 17 newtons. How does the answer to part A, part 2 compare with the upthrust of the water on the board? Well, the board must be supporting that same value. It should be the same value. If we think about the actual board now, so there's the board. We know the board is pushing up with that 17 newtons. So that means that the person must be pushing down on the board with 17 newtons. And so the upthrust from the board must also be 17 newtons. This is a little bit of a Newton's third law question. So we'll study it in more detail in the future. But we could say the board is in equilibrium. So no net force. No resultant. Okay, next question then, part B. Okay, we have a few things going on here. So what have we got? 1.8 meters. He's leaving the place. Okay, right, cool. So we know we can draw a vector. See if we can get that vector a little bit straighter. So we've got a vector here of 12 meters per second. And the angle is 17 degrees. I'll just label it on there again. I know it's already there, but I'd like it next to my velocity vector. Find the speed at which he enters the water. Okay, so we've got to do a bunch of SUVATs, and we've got to do horizontal and vertical. So let's write these out. So the horizontal SUVATs, S-U-V-A-T. What do we know here? Okay, well, we know how fast he's going. It's 12 cos 17. 12 cos 17. We know he's not accelerating, and I think that's about it. We don't know anything else. Let's do the verticals. Notice I'm not worried. The horizontals, I don't know enough stuff. Just means it's not very... I'm not ready to use the horizontal information yet. Let's do the vertical then. So vertically, how far has he fallen? So by the time he gets down to the bottom, as he strikes the water, he's fallen negative 1.8 meters. So I'm choosing upwards as the positive direction. His initial velocity was 12 sine 17. His acceleration downwards was minus 9.81. Okay, so let's see if we can figure out his final velocity here. We should be able to. So we've got SUAV. So v squared equals u squared plus 2as. So v equals the square root of that. So we've got the square root of 12 sine 17 squared plus 2 minus 9.81 times minus 1.8. Okay, let's find out how fast his vertical velocity is. So 12 sine 17 squared plus 2 times minus 9.81 times minus 1.8. Square root it, we get 6.9 meters per second. So we know that he's going downwards at 6.9 meters per second. We know he's going across at 12 cos 17. That speed didn't change, so 12 cos 17. So that's 11.48. Let's call it 11.5. 11.5 meters per second. So now we use Pythagoras to work out the resultant speed. So we do the resultant speed, which we're kind of looking for, our final answer, let's just call it V, would be the square root of 11.5 squared plus 6.9 squared. So this is just Pythag. So squared plus 6.9 squared, square root the answer, 13.4 meters per second. We don't need an angle because it asks for the speed, not the velocity. That's question 2.